I'd like to start by thanking the organizers for all the work they've done and for the opportunity to present our work here today. This work has been ongoing for many years, and I'd like to acknowledge my teammates' efforts, Jean-Lang Huang and Mark Verno within the Canadian Geodetic Survey, as well as my colleagues within the GSC, Hazen Russell and Melissa Bunn, and Aquanti, and in particular Stephen Frey, who provided the modeling results that we'll be comparing to. Detecting groundwater storage changes is difficult to do because we can't see or easily measure groundwater from the surface, and changes in local well levels cannot always be extended beyond the local area due to factors like complex geology or local water usage. Satellite gravity provides a tool that can be used to accurately detect and monitor changes in water at or below the Earth's surface. I presented some of this work 3 years ago at this meeting, but at the time I was only able to compare to groundwater well measurements. And this was a qualitative comparison as variations in well levels do not directly translate to water volume changes. To calculate volume changes, you also need a three-dimensional geological model that includes things like porosity, so you can determine the fraction of the ground experiencing the changes observed in the wells. We've now been able to do this with the help of Aquanti's Hydrogeosphere model for southern Ontario. This model incorporates surface and groundwater observations across southern Ontario, as well as the physics and environmental drivers that produce change. This allows us to make an actual apples-to-apples comparison between the changes in water storage measured using GRACE gravity and those inferred by combining observations with a state-of-the-art hydrological model. The results of such comparisons are important for identifying potential issues and improving both the gravity techniques we use as well as the hydrological models. I always try to include a brief summary of the GRACE satellite mission for anyone not familiar. The original GRACE mission was launched in 2002 and collected data until mid-2017. The GRACE follow-on mission was launched in early 2018 and is still operating today. Both missions consisted of a pair of satellites orbiting the Earth at approximately 500 kilometers. As the satellites orbit the Earth, the path they take depends on the local gravitational field. Any change in mass near the surface of the Earth changes this local gravity field. In the example shown, moving from the left cartoon to the right, there's an increase in the amount of snow at the surface, as well as the amount of water in the ground. This increase in mass results in an increase in local gravity. And the next time the satellites pass by, they take a slightly different path. By carefully tracking the positions of the satellites through time, we're able to infer changes in mass from observed changes in gravity. And once we've removed some of the other known drivers for mass change, such as glacial isostatic adjustment, what we're left with is changes in water and ice at or near the Earth's surface. Due to the high altitude of the satellites, the resolution is at best a few hundred kilometers, and it takes about a month of measurements to assemble a single solution for mass change. So to summarize, we can use these satellites to measure changes in water storage. These changes are on a scale of 300 kilometers, and solutions are monthly. My colleagues and I have been working on this for a little over a decade and a half, and the Canadian Geodetic Survey at NRCan has developed state-of-the-art methods for processing and analysis of GRACE data. We've also done a few things that are really quite simple, but extremely important for studying changes in water storage across Canada. The major GRACE solutions offered from the GRACE Data Science Centers produce solutions using large grids in which the grid cells are 200 to 300 kilometers in size, consistent with the GRACE spatial resolution I mentioned earlier. They then interpolate to provide higher resolution grids for hydrological work. On the left, I show the analysis geometry for what I'd consider to be the most popular GRACE solution used today. It's from NASA's Jet Propulsion Laboratory, and you can see the size of their solution grid cells. And in regions like the Great Lakes, you can see that these grid cells overlap with both land and lakes. Our solutions incorporate drainage basin geometry, and I'll show you later in the talk how much of a difference this can make. So why look at the Great Lakes region in southern Ontario in particular? One of our biggest questions within the geodetic community is how accurate is GRACE, and how far can we push the limits of this data? To test our best methods for detecting water storage changes, we need an area where water storage variations are large, reasonably well known, and at a spatial scale comparable with the 300 kilometer limits of GRACE. The Great Lakes Basin is perfect for this. The Great Lakes themselves are big enough that changes in water level are easily detected with GRACE. And these exact water volume changes are well known as they're accurately recorded by gauges. Furthermore, this is an important area as it contains a large internationally shared water resource, and it's one of Canada's most populous regions. So there are dense surface and groundwater monitoring networks, and sophisticated models have been developed for the hydrogeology here. The map on the right shows the Great Lakes region. The green region is our analysis region for southern Ontario. The red squares that overlap with the green region show the borders of the grid cells from some of the other GRACE solutions that I'll also show. GRACE measures the total water storage change within a region. This is the sum of changes in surface water, snow, ice, soil moisture, and groundwater. We'll compare our results from GRACE to Equani's Hydrogeosphere model for southern Ontario. Their model includes some of the most detailed three-dimensional geological information available and uses a physics-based approach for calculating water transport. The model is calibrated with local observations and forced with historical weather and surface data. From this model, we can easily extract and add up the contributions from changes in surface water, snow, ice, soil moisture, and groundwater. This produces a total volume of water change for the region that can be directly compared with what we see from GRACE. The plot at the bottom shows the modeled contributions to total water storage change for snow and ice, surface water, soil moisture, and groundwater for the period from 2002 to 2016. So here are the results. The black line shows our GRACE estimates for changes in total water storage over southern Ontario for the period from early 2002 to just a few months ago, so up until November 2021. The blue line shows the variation calculated using the Hydrogeosphere model. We're very happy with the level of agreement that we're seeing, both in terms of absolute amplitude as well as the close match in seasonal timing. In fact, the agreement is much better than I had personally expected. Between the complexity of extracting such estimates from satellite gravity data and all the complexity and uncertainty that goes into building a sophisticated hydrogeological model like HGS, I was hoping they would just be close. But I think it's fair to say that the agreement's better than close, and this is therefore very strong validation for both approaches. From the GRACE time series specifically, we can see a few things. The first is that there's a very regular seasonal cycle with a peak-to-peak amplitude of about 10 to 15 cubic kilometers per year. The lowest storage from GRACE was observed in 2012 with other significant lows in the early 2000s, 2011, 2015, 2019, and 2020. Highs were observed in 2011, 2014, 2016, and 2018. Highs occur during the winter and tend to last several months, sometimes into spring, and lows occur in late summer and tend to last for a shorter period. And probably most importantly from this, we do not see any significant long-term trend for southern Ontario. I want to show you what happens if you do the same calculation using GRACE data from a solution that uses a simple grid for their analysis regions and then interpolates. This is shown on the bottom. The blue curve is again the estimate from the hydrological model, the exact same one that's shown in the top plot. The red and green solutions are GRACE solutions from NASA's JPL and the University of Texas's Center for Space Research, two of the GRACE data science centers. These solutions both use simple grids, are considered to be state-of-the-art, and are used widely for hydrological problems. You can see that there's far less agreement now. Solutions show a significant increase in water storage over the past few years, one that correlates with lake level increases, and you can also see that there's a significant phase shift or time lag between the model and the two GRACE solutions, with the GRACE solutions lagging behind by several months. This is simply due to the geometry that they've used in their analysis. Their coarse analysis regions overlap both southern Ontario and the surrounding Great Lakes themselves. So you end up with part of the lake level change signal leaking into the southern Ontario signal, and you get a very different and incorrect solution that tells a very different story. Our solution, which uses analysis regions constructed from Canadian drainage basin geometries, largely avoids these issues. And in contrast, and as I mentioned earlier, our solution shows a far more regular seasonal signal with little correlation with the lakes and little to no long-term trend. From a water management standpoint, this different conclusion is very important. There is maybe a hint of a weak negative trend in our solution, but it's very small, and I'd want to see a few more years of data from GRACE follow-on before we could probably call it statistically significant. So the purpose of this comparison is to show that we need to be very careful analyzing and interpreting GRACE data, and we need to pay attention to the details. In Southern Ontario, we have a nice model to compare to and to check our results, but for most of Canada, we don't. Okay, so coming back to the comparison above, I mentioned that there's good agreement between the model and our GRACE estimates, but there are also some differences. We can split the time series into two segments with a split around 2007 to 2008. For the latter times, the agreement's very strong. For the earlier times, there's some more significant deviations. The timing or phase of the signals still matches well during this earlier period, but there are some amplitude differences. On the bottom, I'm again showing the different water storage components that come from the HGS model. And what you can see is that the groundwater component coming from the model also seems to show somewhat different behaviors for these two time periods. So we're currently looking into this. But this is an example of how we can use GRACE to help validate models, as well as to identify specific parts of models that may still need a little tweaking. And any improvements in regional scale modeling are likely to translate down to improvements in local scale results as well. So for a summary, GRACE can be used to detect and monitor regional scale changes in water storage. While we can't technically say we've proven that our GRACE results or the modeling results are correct, the strong level of agreement between the two results which are independently derived using different data and approaches, is a very strong validation of both. GRACE can provide constraints on total water storage change that can give us new and important information on a region and can help to constrain or validate models. It can tell us how much water change there is, whether there are significant trends, what the strength and timing of the seasonality is, as well as how regular all these things are. To wrap up, I'll just say that we're extending this work as part of the Canada One Water Project, which you've likely already heard a fair bit about over the past couple days. The plan is to use GRACE to assess total water storage changes nationally and to help us constrain the various models that are produced. Thank you for your attention. I'm happy to answer any questions or discuss, and if there isn't time, please send me an email.